All right, folks, just let me know if you can hear me okay. I'm going to present the presentation. All right, so you should be seeing the first slide of just a very short presentation on 10.1 quiz Q&A webinar. We're going to be mostly taking your questions and answers. Just want to double check. We're at 7:45 now, so let me know if you can hear me. Just give a yes, and if it needs to be louder or softer, hopefully you can adjust on your end. But for me, just let me know if you can hear me, and then we're going to get started right away. I see we have several people joining us on this webinar, including we have Julia, we have Ryan, Ola, we have Tommy with a very interesting greeting, as well as Eric, Lydia, Alex, who has figured out how to do a different kind of icon in the top right of the Google Doc. Alex, you might have to share that trick. We have Alice in very bright and vibrant pink tonight, and we have Courtney and Andrew. Andrew with an emphatic hey, hey, with 3 exclamation points. Excellent. All right, so hopefully you can hear me. We're just going to go ahead and get started on the quick presentation. This will just be about 3 or 4 minutes, and then I'm going to open it up to your questions. So as I'm presenting, you can go ahead and start typing your questions into the Google Doc. Maybe you want to have a split screen open with another window, and then when your question is on, you can watch the video live. But as you can see, this section 10.1 is on power series. We talked about infinite series, and then power series in particular. And there's a bunch of terms and definitions you're going to have to know. So I'm just going to take one more quick check at the Google Doc. Okay, great. People are starting to ask questions. And then we can look at a few of those together. Perfect. So what is a power series? Well, you should know that definition from your notes. It's basically when you have terms that are where the powers of x are increasing. They're not negative. They start out at 0, and then they increase. The exponents of x increase by 1, and then there's just some coefficient in front of it. It could be 1, it could be anything, but that's what a power series is. You have increasing powers of x. 4 series you're expected to know. I just copy and pasted this. I cropped it from the study guide, but it'll definitely be beneficial to you tomorrow, especially on the multiple choice, to know these 4 series by heart. Okay, so maybe make 4 index cards or practice writing them down a few times. The first one you should know, it looks like that a over 1 minus r formula. The second one, e to the x, we showed that in class, or we were given it and we investigated it. And that's the only one that e to the x is special, because that works on all values of x, negative infinity to positive infinity. That is the only one that converges. This equality holds, rather, for all of those values of x. The other 3 only hold between -1 and 1. Okay, and then we have inverse tan and ln of 1 plus x. These last 2, technically don't have to memorize them. If you want to just have a sketch in your mind of how to derive them, you could. For inverse tan, the derivative is 1 over 1 plus x squared, so you can set up the a over 1 minus r with 1 over 1 plus x squared, and then you will get a series for that and integrate it to get inverse tan. And with ln, it's the reverse. You're going to take the derivative, and you'll have 1 over 1 plus x. You get a series for that, and then you can integrate as well. Actually, yeah, both of these are integration to obtain the series. You'll get a series, and then you'll integrate it to get the series that you want. There was one we did in class, not one of these 2, where you can use a derivative. And that's something that could come up. Okay, but those 4 you definitely need to know. We're going to add to that list for the AP test. There's about 7 common series that you're expected to know. Here's another quick tip before we head over to your questions. Know the 2 tests for convergence and divergence, particularly number 1, the nth term test. And then this is the contrapositive that I've bolded, because that's really where the test comes into play. And it says, if the limit of the nth term does not equal 0, then the series diverges. be extra careful because the converse of that is not true. Okay, it's not true that if the limit does equal 0, then it converges. We actually don't know that. We know two things. We know this statement that if it does not equal 0, then it diverges. And we also know the contrapositive of this. If you flip it and negate it, we know that if it converges, then the nth term, the limit of the nth term will equal 0. But we don't know that if the limit of the nth term equals 0, then it converges. That we cannot conclude. If the limit happens to equal 0, then we need to find out in some other way of whether it converges or diverges, perhaps using the geometric series test. Okay, so but it does work this way, so you should know the logic behind that and how to use it. For the geometric series test, that one, if you're given a series, is a little bit more straightforward. You're simply testing if the common ratio, the absolute value of the common ratio is less than 1. We have convergence. Otherwise, we have divergence. Okay, so that was just a quick review of a few concepts, and then obviously you should know the rest of the items on the study guide. But thank you for joining us, those of you who are here, and let's spend the rest of the time with your questions. I'm going to open up Sketchpad and kind of share my screen with you. So let's see if we can make this work, and then we will answer as many questions as we can. Let's see where this is at. No, that's not what I want. Bear with me for a moment. Okay, here it is. And you are screen sharing. Okay, stop screen sharing. Hello, folks. Now I am going to give you my entire screen, which will have your questions here. And I can open up Sketchpad side by side. Okay, and I'll try to make this larger so you can see what I'm talking about. So let's go to your specific questions. And there were Alice and Eric caught some board points today. So if you didn't have a chance, you can check up on the email. I might reference those. But okay, we have a first question. Can you please go over how to find a power series when x equals a, like in set A2, questions 31 to 34? Okay, let me flip to that. 31 to 34 in set A2. Okay, hold on, let me just double check. I'm looking at the right thing. Okay, so let's just take an example here, and I think if we walk through it together, that'll be helpful. So let's just, if you have a particular one in mind, that's fine, but let's just look at 31. And in number 31, a lot of these refer you back to previous exercises. That's why I was taking an extra second just in my notebook to see what I did. So 31 refers us back to exercise 21. And exercise 21 is giving us this series. So exercise 21 is going to define our function f of x as the following geometric series. So we have n equals 0 to infinity, 2 to the n, x to the n. I'm just going to rewrite it as 2x to the n. And just to make the geometric nature explicit, and we know that this converges to 1 over 1 minus 2x. This is the geometric series formula, a over 1 minus r, when the absolute value of 2x is less than 1. Okay, so this, I'm not answering the question yet, I'm just setting it up. This was exercise 21. Oh, okay, one problem had x equals 0. Okay, I see Julia is clarifying her question. One problem had x equals 0, the other had x equals a. I see the question. Okay, so that... Oh, okay, sorry. If that's your question, so the a, like what is the a? If that's what you're asking, like this a to x, the center, and I'm glad you asked this because I don't think this came up clearly in class, but it was on the homework. The center is just the number in the middle of the interval of convergence. So the center of, let's see, for number 32, for example. I think this might clear up your question, Julia. And then if you want me to walk through it, I can. But the center of number 32, since the interval of convergence was this, 0 less than x less than 2, we simply say the center is just the number in the middle, or the midpoint of the interval. So in other words, a would equal 1, because 1 is halfway between 0 and 2. So the center of an interval, or the center is simply the middle of the interval of convergence. Okay, does that make sense? I'm just going to say on the Google Doc, a, or the center of the interval of convergence equals a. So you first find the interval of convergence. You could solve this inequality up here depending on which one you're doing. And then the center of it is simply the number in the middle. Okay, so good question there, because that did not come up in class, but it was in this jam-packed section. And notice 10.1, there's a lot of material in here. Each of these sections with series does have a lot of material, but 10.1 is particularly lengthy as they're laying out the beginning groundwork. All right, we're going to go to this question from Alice. Can you explain the difference between a normal power series and the geometric ones, like the ones in numbers 54 to 60? Okay. Well, I hate to disappoint, but what can I say about this? Okay. So geometric and normal power series. Yeah, so I'm gonna phrase this. Yeah, so a geometric series, and I don't think this is going to affect your answer to any of the questions, but basically the question is, what's the difference between geometric series and a power series? Okay. So a geometric series is any series that takes the following form: n equals 0 to infinity of a times r, to the n. Okay, where a is some constant, whereas a power series takes the form you know what? The reason I'm struggling to distinguish this question, it's a good question, Alice, is a geometric series is very similar to a power series. You might even say that it's a type of a power series. I'm looking if the book makes a distinction, but from what I can see, and this shouldn't really affect any of your answers, but a power series can be used to represent a function because the variable is x that we use, whereas a geometric series, they define on the previous page, they just show it as a times r times r Oh, you know what? There is a difference. Okay, here's the difference. Okay, in a geometric series, the next term can always be obtained by multiplying the previous term by the common ratio. Okay, this is exactly the answer. I'm glad you asked that because I actually didn't have a clear distinction in my mind until just checking that right now. But in a geometric series, the next term will always be obtained by multiplying by r. You do times r, make this clear, times r, and you always get the next term. Whereas in a power series, the x terms are increasing by, the exponents of the x term are increasing by 1, but this coefficient can be running on a totally different track, meaning we're not told how these coefficients are determined. They could be increasing by 1, for example. So you don't have that guarantee. Oh, this should be equals here. You don't have the guarantee that each term is a multiple of the previous term times a common ratio. Okay, so that's exactly the difference. Let me just reiterate this. For a geometric series, you know that the next term, each term is equal to the previous term times r, times the common ratio. With a power series, that's not necessarily true because the coefficients could be running on a totally different track. We're not told how the coefficients are determined just by knowing it's a power series. We don't have the guarantee that it's equal to the previous term times x times x times x. No, we don't know that that works. It might work. So some geometric series, or how can we say it? Some power series are geometric, but not all power series are geometric. Okay. And we also have a clarification underneath from someone in dark blue. Looks like Ryan has asked, in the notes, isn't the formula for geometric series a to the r n minus 1? Can you please clarify the a to the times r to the n versus a times r to the n minus 1? Oh, Courtney. Thank you, Courtney. Let's see if I can clarify that. You know, honestly, n minus 1, n plus 1, it's always going to depend on the context. You could say that this is a geometric series, and I would start it at n equals 1 to infinity. But you could also say that this is a geometric series, and I would start it at n equals 0. So it depends where you start. If there's a specific portion in mind, Courtney, that you are troubled with, an example, just let me know. But basically, the indices can always be rewritten, or you can re-index and start at different values and then just change what's inside the sigma notation, and you can come up with a valid series. So it depends on the context. But that's a good question. Okay, so hopefully that made sense. And Alice, if I didn't answer your question, let me know. But I will just add a note underneath it. Let's follow this. I'll just put a quick bullet point for these questions. So we answered, oh no, that just messed up the numbering. Okay, so for this one, we'll say not all power series are geometric. All geometric series are power series. And see the specifics of that, it has to do with the coefficients and the common ratio. For Courtney's question, okay, we're good. It depends on how you index it. Let's see, we have another question here asked by, I think, Julia. And that is, what is an example of a problem that would require the nth term test? Okay, good question. Because as I remember doing the homework, most of them, if not all, could be done with the geometric series test because they happen to be geometric. So one that might require the nth term test would be something that is not geometric, particularly, I'm just going to look for an example. Looks like page 489, number 28. No, number 18. Page 489, number 18. You're given a series of a half plus 2/3 plus 3/4 plus and so forth to n over, they give you an nth term, n plus 1. Good question, Julia. This could definitely show up tomorrow. So, and the question is, does it converge or diverge? Okay, does it converge or diverge? It's not geometric, so we can't use a geometric series test. However, we can test the nth term by looking at the limit as n goes to infinity of this, n over n plus 1, which is simply a polynomial. And the degree of the numerator is equal to the degree of the denominator. So we take the quotients of the leading coefficients, quotient, and it equals 1. So since the limit does not equal 0, we can conclude that it diverges. Okay, and this is a scenario that holds under the nth term test. That's just one example. Okay, we have a couple more questions coming in. Feel free to go ahead and ask away. We got about 10 more minutes on my clock, but I can extend it a few extra minutes if you have questions that are not answered. And then I'll post this replay for anyone who wants to review it later. Okay. Okay, number 5. Looking at this question, I think this is Alice. Why didn't we have to integrate or differentiate to find the power series for problems 54 to 60? I think we did have to differentiate or integrate, but let me relook at that. For 54 to 60, okay. Oh, I'm sorry. I was thinking of different questions. Okay, yeah. So this goes to the. You definitely don't have to differentiate or integrate there. This goes to the idea of a over 1 minus r. If you can make something look like a over 1 minus r, then this just does equal the power series n equals 0 to infinity of a times r to the n. Okay, that's just the case. If you have a geometric series, if you have a fraction that can be rewritten like this, or a function that can be rewritten like this, it just equals straight up that geometric power series. That's the formula. No differentiation or integration needed. You just would have to say it holds when the absolute value of r is less than 1. So in number 54 through 60, the only goal, or the only thing you have to do, is make the fraction look like this form. Rewrite it so it looks like a over 1 minus r, and then you automatically know it equals the power series. It equals the geometric series, which is also a power series that I wrote over here. And so that's your answer. Okay, the legwork is you have to sometimes do careful algebra to rewrite it. And when you have to find the interval of convergence, you have to take whatever term is in this position. After you rewrite it as a over 1 minus r, this term r is used to find the interval of convergence. Okay, so I hope that answers your question. I'll just say it directly. You use a over 1 minus r and rewrite the functions in that form. And once you do that, it just directly equals the geometric series. No integration or differentiation required. Can you restate the contrapositive of the nth term test and what it does and does not guarantee? Well, I will direct you to the replay, but I will say it one more time. What it's given in the book, so I actually said, I give you the statement on my PowerPoint slide is the statement you should memorize. Okay, so why don't I just say this? This is the statement you should memorize. If the limit as n goes to infinity, if the limit does not equal 0, this implies divergence. Okay? This implies divergence. This was the contrapositive in your notes. This was the contrapositive part. This is the part that you should memorize. What I also gave you in your notes is the original theorem says that if we have convergence, then this implies that the limit of the nth term is 0. Okay, so if you want to memorize, these are the two statements that are true. The top one is more useful. Okay, but these are the two that are true. What's definitely not true is the converse of this second statement. So I would say memorize this, number one. You can also know that this is true, but where students will get confused with the logic is reversing this one. They'll say, oh, the limit of the nth term equals 0, therefore I know it converges, and that's not true. So the nth term test really only helps you test for divergence, and if it doesn't diverge, then you actually need to go about some other way of determining convergence or divergence. Namely, the only other way we have so far is the geometric series test. In the future, we're going to have more tests. So I'm just going to say C presentation for this one. Okay, when would the power series, when would the e to the x power series be useful if the integral and derivative of e to the x is itself? Okay, good question. It's actually going to be more useful a little later in the chapter, but for now, you should just know that this is the power series for e to the x. It starts with 1 x, x squared over 2 factorial, x cubed over 3 factorial. And the person who asked this question, you're correct, that if you integrate this series or differentiate this series, you get the same thing. By the way, that's an alternative proof for the fact that the derivative of e to the x is itself an integration antiderivative of e to the x is itself. You can simply look at the derivative or integral antiderivative of the power series. But just so you know, I mean, what's coming down the road, if I asked you to represent something like, or later on in this chapter, we might say, okay, I know you know this function, but what about, can you rewrite this function as a power series? Okay, and what you're going to do later in the chapter is not tomorrow's quiz, but you'll give, just given any arbitrary function, you have to use your base knowledge of the other functions to rewrite them as power series. Okay, so for now, you just have to know it as a fact, know what the E series is, e to the x, and how to identify it. But in the future, we're going to be using that to build other series. Okay, yes, I meant to talk about this. I think Alex just asked, can I do one like number 53 on the study guide problems? And the answer is, I just want to double check this was the ones I was thinking of. I actually made a mistake. Yeah, I apologize for that. 53 and 54, they require tests and analysis of series that are in later sections. So you can omit number 53 and number 54. One thing I will say, though, if you're not sure what the series looks like 53 and 54, they look a little mysterious. And, you might not know what they are. Write out the first few terms. That's something we learned from one of the trig ones that Stephanie brought up in class on the homework. Write out the first few terms and you'll get a sense for the series. But for 53 and 54 on the review, you can omit those. We'll cover that when we get to later series analysis. Okay, so we're just about at 8:15. If you have any last minute questions, you can throw them right down in the doc. I'm happy to stay around for another 5 minutes or so. And we can go from there, but hopefully you reviewed your homework problems, practice write down your series. We could do that. Okay, when would we use, Julie's asking a good question. When would you use the power series for tan inverse of x, ln of 1 plus x, and e to the x? Okay, why should they be memorized? I will say for tomorrow's quiz, it's just a matter of knowing the basic facts. It's kind of like when we first learned derivatives. You have to know the derivative of tangent is secant squared. You have to know the derivative of secant is secant x tan x. So they're just basic facts that need to be known. What I can also ask Julia, and just keep in mind, I could ask you to derive either one of these. That's right in our notes. Like, can you find a power series for this? Or can you show that the power series for this equals what it does? And to do that, you're going to have to know the methods of, the derivative of this, the derivative of ln of 1 plus x equals something that looks like a power series, or sorry, something that looks like a geometric series. And so if we can find the geometric series, then we can integrate it, and then we'll have a representation for ln of 1 plus x. Same thing with inverse tan. It's actually the exact same process. So for tomorrow's quiz, you have to have them memorized for basic facts of series, just like integration and antiderivatives, or just like differentiation and antidifferentiation. You just got to know your basic facts, but also you need to know the process of how to get them. Oh, I see what you're saying. Yeah, could there be a problem? That more for the future. For now, it would be like, can you identify them and can you derive them? If I said, like, show where they come from. But in the future, this is kind of what I was saying before. We're going to write a power series for any function. So say you had to write a power series for 5 plus x. Okay, we're going to be using our base case and then modifying it in order to write the power series. We would kind of rewrite this as something like ln of 5 times 1 plus x over 5. This is later in the chapter. You don't need to know this for tomorrow. But then we kind of use some log properties to split it up. Ln of 5 plus ln of 1 over x plus 5. Sorry, 1 plus x over 5. And then this second part looks like the series we know that we can use, and then we just have a constant added on. So the short answer is you need to know them as basic facts and derive them. In the future, we'll use them to build other functions, representations for other functions. How are using sine and cosine solved? Is there any formula to be memorized? We will have series for sine and cosine, but they're not in this section. So in the future, we will have a series representation for sine and cosine. For now, Courtney, the only type of sine and cosine problem would be, ones like the homework where, number 15, for example, it just had a cosine inside the series. And we're asking about, convergence or divergence. It was cosine of n pi. And they're saying, does this converge or diverge? This is another one, by the way, where the nth term test is good. You could take the limit of the nth term and then cosine oscillates. So since the limit doesn't converge to 0, then we know that the series diverges. So for now, sine and cosine, they could show up inside of a problem, but you won't have to represent them using a series. Okay, so those are excellent questions. We're just at about 8:20, and I appreciate anyone who showed up. Hopefully you got something out of it. If not, I refer you back to the study guide and a couple tips in the presentation. The problems you're going to see tomorrow are, some are just, definition based. Do you know what this series is? And then others are, convergence, divergence, interval of convergence, things that are on the study guide. They're not quite exact questions. Some of them are, maybe one or two are sample questions that you would see on the AP test yet. But since this is just the foundation, we actually haven't gotten into what are called Taylor polynomials and Taylor series. And when we do that, that'll be in section 10.2. Those are the most common ones on the AP test. For tomorrow, this is a foundations quiz on the beginning of series. Okay, Also, Gary's hello was AFK. I don't know what that means, but perhaps it means always for always no. Oh, away from keyboard. Yes, he was away from his keyboard. What a sad reality. Well, hopefully Gary will find his keyboard and you will be ready for the series test tomorrow. Quiz. Okay, well, any other questions going once? Let's start typing something in the Google Doc. Feel free to email me later. I'll be in at about 7:45 if you have any quick questions, but I'll post this to the classroom and you can take a look later. All right, so any other quick questions going twice? And sold. Okay, folks, thanks for joining us. Have a good night and good luck in your studies.